Okay, as we continue our coverage on plastics, this is phase three, part three. Um, we're going to build the proverbial hydrocarbon backbone of most all of these thermoplastics um, by displaying the ethylene gas monomer. But before we go into that, I've listed up here the really of all of these literally hundreds, almost thousands of different types of thermoplastics that are available to the design engineer nowadays. And by the way, thermoplastics make up for almost 70% of most of the volume of plastics utilized in society. So it's a big business and industry. The usage and designing with these thermoplastics. So at any rate, there are only about 5 or 6 different elements that go into most of these polymers. And I'll list them here for you: carbon, hydrogen, nitrogen, oxygen, fluorine, and chlorine. And we'll show you some examples of those. But first, let's look again, go back to this hydrocarbon backbone of ethylene gas. And again, we told you that we get that from natural gas, and that's why there's so many plastic facilities, manufacturing facilities all along the Texas coast. All right, so be that as it may, so here it is. I showed it to you last day in sort of a format. So with 2 carbons and 4 hydrogens, and now what takes place all within this boundary right now, these are all covalent bonds. They're all sharing of the electrons here, because carbon needs 2 and hydrogen needs 1. And so you link up the 2 hydrogens with the 1 carbon and everybody's happy. And then you have these 2 double bonds between the carbons themselves to form this C2H4, which is ethylene gas. Now, during this process that these chemical companies have to polymerize this, they react this gas with what they call an initiator or a catalyst, which basically breaks open that carbon double bond and allows it to have a side chain or a side bond on either side of this carbon, which then when this ethylene gets polymerized in this process, it turned from ethylene to polyethylene, because it went through a polymerization process. So now they call it polyethylene. So this is the basic backbone monomer, the ethylene monomer that's going to turn into a polyethylene as soon as we start adding this number of repeating units, which this is a repeating unit. And so in this nomenclature, this notation, this N will always equal the number of repeating units, which is what we're going to call the degree of polymerization. How many of these are going to be stacked together in this chain? And this is very significant in this long chain formation of how many are going to be in there. But these are going to be the repeating units right here. And this is the notation that the chemists have come up with in noting that this is a polymer monomer or a monomer of some sort of polymer that's going to be produced like this from ethylene to polyethylene. Again, it shows the same thing over here, but it does show the breaking up of that double bond and with the 2 side bar bonds over here. Now, as I said before, all within this confines of these brackets, this is all covalently bonded elements. But it's when they break this bond up, the 2 side chains, sidebar bonds here, the electrons, or what we call a van der Waal bond, So, and that's a fairly weak bond, and because the individual monomers can be broken when they're chained together, the actual link, weak link in the chain, so to speak, when they can be broken fairly easily because of the type of bond that it is. It's not a really strong bond like the covalent bond might be or the ionic bond might be. So that is why, structurally speaking, that's why plastics are not nearly close to the strength of metallic elements or metallic materials. Because the bond strength is just not there in the van der Waals bond as opposed to ionic, covalent, or of course even better, a metallic bond. Okay, so this is the notation. This bracket denotes this monomer notation, and this n will equal the number of repeating units. How many of these will be stacked up in a chain? As I told you before, this n could be anywhere from 10 to the third to 10 to the sixth number of repeating units. Okay. Now, to show you that this is sort of the backbone of a lot of these hydrocarbon-based polymers, we're going to take this backbone, we're going to do a little rearranging, but simply keep the same structure intact. So again, here are the two carbons, and here are three hydrogens, or no, two hydrogens, and we're going to replace, I think I messed this up here. Let me look and see right quick. On this one. Okay. Yeah. Okay. Here somewhere. Okay. Yep. Okay. So I messed this up, folks. Thought that was supposed to be another hydrogen in here. All right. Sorry about the delay. So there's another hydrogen. So we replaced one. Essentially, what we did was we placed one of these hydrogens with a chlorine. Okay. So when we do that, you see, we basically keep this structure intact, but just change one of the hydrogens for a chlorine, and then we come up with, this was a chlorine monomer, and we polymerize it, we come up with a polyvinyl chloride, or PVC. So this is the structure, the monomer repeating structure unit for PVC, right here. 3 hydrogens and 1 chlorine. Now doing the same thing, keeping this intact with the 2 carbons, but changing all the hydrogens out and substituting fluorine, we come up with a very interesting and unique polymer called polytetrafluoroethylene. Polytetrafluoroethylene, PTFE for short, but even shorter, you'll recognize the name as Teflon. Okay, so that is Teflon. 2 carbons, 4 fluorines. All right. And the N here is significant, all right, very significant. Just like in this, because this is just polyethylene, we have a variety of polyethylenes, and it's all predicated on how many of those N's are involved. Okay, so we have polyethylene. In the polyethylene family, we have usually called low density, which is just LD, is noted LDPE. Then have high density, which is denoted HDPE. And then there's another one called linear low density, but it's not as nearly as prevalent. But the other one that is worth mentioning is called UHMWPE, and that stands for ultra high molecular weight polyethylene. UHMWPE. Now that is where we come up and get into this range of repeating units, massive amounts in this UHMWPE, and we'll talk more specifically about that when we get into the industrial applications. But these are just 3 basic types of potential polyethylene type plastics that, but again, predicated on what this looks like. Okay, now let's see where we want to go from here. First of all, we're going to erase this because now we want to talk about molecular weight, a little bit of molecular weight and what it does to the polymer. So I'll erase all of this. All right. Okay. Now, let's look at trying to look at the molecular weight. And for polymers, the molecular weights are directly related to the number of repeating units. Okay, and that number of repeating units, obviously we were calling earlier n. So therefore, it's also related to the actual polymer chain length. How long is that chain is with all these number of repeating units here? And so many times the chain length and the molecular weight, the chain length and the molecular weights are kind of used interchangeably when talking about these polymers. All right, now let's look at how this works. For instance, if we go back to the C2H4, okay, well, and let's say let's just go ahead and draw this in its monomer form here. And let's leave this N open for the time being. Okay, so you would think then, to try to find the molecular weight of a polymer, what you need to do is first find the individual weight of the monomer, which is going to be comprised, of course, of the atomic weights of the elements that are involved in that monomer. And so if you look at this, obviously carbon equals 12, all right, and of course hydrogen equals 1. Okay, so obviously in this we have 2 times 12 plus 4 times 1, and of course that's going to be 28. All right, that is the grams per mole, or that's actually just the atomic weight of this monomer is 28. All right, so therefore, if you take and you just increase this to make 1,000 of these, connect 1,000 of these, then it would be roughly times 1,000. Then you're kind of roughly about 28,000 grams per mole, but per mole here, as far as the units go, and that would be the molecular weight. Generally speaking, I mean, it's fairly straightforward. If, and it's a big if it was in a perfect world, if we live in a perfect world, and of course we don't. So, and because of that, we have to do something that comes up with what, because the fact of the matter is, there's almost, well, it is impossible to exactly count the number of repeat units when you're producing these polymers. I mean, you can get a range sort of, but you can't get an exact number. So this number cannot be an exact number, like this cannot be an exact number. So therefore, what we have to strive for is to establish or find/establish, and what we call average molecular weight. Okay, an average molecular weight. All right, now Okay, so that is done in a sort of a different process. Um, and there goes the bell. And that process is going to utilize something we're going to refer to as the melt flow index, or the MFI for short. Now, essentially, I will explain this what it is, but essentially, what we do is we take a polymer and a solid polymer. And by the way, these polymers come to a manufacturer from the producer. If you're in the business of injection molding parts, okay, let's say you were making all these pencil sharpener bodies, look like this little plastic thing. You're making these. Okay, you'd be getting a whole bunch of these clear plastic pellets, and you'd be getting some other plastic pellets, the same exact polymer, but they would still be clear, but you would add a blue colorant chip to get the bottom portion of this in the injection process. So you'd have both clear and color in two different molds. All right, and then you just put them together. All right, well, at any rate, it would be solid little beads. They look like little tiny beads, maybe anywhere from 3/16, well, not quite 3/16, a little bit less than 1/8 of an inch might be little tiny round beads, or sometimes they're more, they're not quite at round, but anyway, so that's what they come to the producer in, kind of like real tiny little BBs. In fact, that's kind of what they look like, tiny BBs, except they're polymers. All right, so at any rate, they come to them, and then that's what they melt and then liquefy and then inject under pressure into an open cavity closed mold. But be that as it may, what we're going to do with this this melt flow index value is, the way we get it is we take it and we're going to put it in a little device. It's a heater device, and actually, let me show you here. I actually have a schematic of one of these, and before I do that, let's put this on here. That the MFI is probably the most common parameter. The most common parameter specified when describing a polymer. When describing a polymer, okay, this MFI is the most common parameter specified, and it's primarily because of its processability. Okay, its processability. Now, this is what it looks like, and let me see if I can. Okay, this is what it looks like right there, and I made a little note there in red for you to look at that. But essentially, what's taking place is that all of that polymer, the little plastic pellets, are in this heating block, and they heat this up, all right, and then they've got this piston with a weight on it, and then they let it go, and this is a tiny little orifice down here, and so they have a timer, and of course they heat at the right temperature so it liquefies it, and then they let this weight go, and this piston presses down on this polymer melt. We call this a polymer melt now, and it squeezes out this liquid polymer, all right, but as soon as it starts to come out of here, of course, it's going to start to solidify. And so, and what they call this is an extrudate, polymer extrudate, all right? And it's coming out, and what it's going to do is it's going to end up on a platter, all right? And then at a certain time, they're going to stop it, close the orifice, and simply all they're going to do is weigh it, okay? And so the relationship is that when you have a high melt flow index, all right, it indicates a low molecular weight, because that means it has a much lower viscosity because a lot of it got out. If it had high viscosity, not much would have gone out, and you'd have a low melt flow index, okay? So ponder that thought for a little bit, but I've got to shut this down. So we'll go back to this and reinforce this on the next slide, and then we'll continue on with polymer crystallinity. Okay.